Okay, all right. So this is another example of a system with multiple boxes and a pulley, which has to be accounted for now because it does involve torque. So if you want, go ahead and read all the different parts there, color coded for you, and maybe take a screenshot of this so you can reference it as I kind of go through each part individually. So the first thing you should always do is draw a free body diagram and identify all the forces present for each of the mass and the pulley. So if you can kind of just follow me through the animation that pops up here. So for the hanging mass M2, there's a vector there that indicates the weight, aka the force of gravity due to mass 2, and that vector is directed down the page, and it's going to cause the system to move to the right. And opposing that particular hanging mass, it's going to be this particular vector here, which is drawn a little shorter because it is technically a little smaller. And I'll call that T1. And now that the pulley has a mass, each side of the string has to have its own subscript. Just the forces will be behaving differently based on whether you're assessing the pulley or the hanging block. So you have also T1, which will cause the pulley to rotate clockwise in this particular diagram. And then if you're looking at the other side of the string of the pulley that connects the pulley and M1, which is green, there's a tension T2. I'll just keep that as T2 in the order of the subscripts. But then again, each side of the string has to have two opposing arrows because they behave differently based on which body you're assessing. So T2 is going to want to rotate the pulley counterclockwise, and then T2 is going to want to pull the green box M1 to the right. And then last but not least, you have your opposing force, the kinetic friction. In this particular diagram, it has to point left because the system is going to be dragged to the right. So that'll be our kinetic coefficient, which would produce a kinetic frictional force there in orange in terms of the color coding. Okay, so I'll just take a part 1 or part A here. So part A asks you to calculate the magnitude of the acceleration of the hanging block. Or just block, not plural. So the hanging block in this case would be M2. So the first thing you should do to make yourself, to make your life easy for these types of problems is kind of to set up the physics for each of the body. So here I have M1, M2, and the pulley. So if you set up the physics for each of the body, and you can kind of see that there's a systems of equation, and usually for most of these problems, they'll just force you to do substitution, as you see here, if you pay close attention to my work in the boxes here. Okay, so if we set up M1 for Newton's second law, we have sigma F equals ma. So the net force will generate, the acceleration of M1. So in this diagram, if you look at M1, which is green, sitting on the flat surface, you have T2 wanting to pull to the right, and then there's Fk opposing it. So here I have a statement that says T2 minus Fk equals M1a. Again, this particular sign already indicate that the frictional force is opposing it. So don't plug in another negative sign for Fk, as this sign is already indicating that. Okay, so don't undo the direction of the Fk. So pay attention to your signs. And then if we do that, you notice here, you can expand f of k into mu k f of n. But for M1, which is just resting on a flat horizontal surface with no additional applied forces, the relationship between f of g and f of n must equal. So that allows us to substitute in for f of n, as we don't know what f of n is, but we can make a statement that f of n, which is this purple vector, must have the same magnitude as this f of g1. Therefore, we can replace fn with m1g. Nothing else in the statement changes except for that substitution there. And as you see, if you substitute all the variables given, you have a 0.2, the mass is 5, and the acceleration due to gravity is 9.8. Again, the negative sign is already accounted for, so you do not need to plug in the negative sign in the negative 9.8. Otherwise, you make this whole entire term positive, because if you have a negative sign there and you plug in another negative, that'll make the term positive, which is not the case, because again, it's f of k is opposing, and that particular sign in front already take care of that statement for you. Okay, and then you notice that you have a T2, which is unknown, and then you have an A, which is unknown. And again, these problems will force you to kind of do substitution, which is a pretty fundamental skill in physics here. So if you set up the function for M2, again, same starting point, but for M2, we notice here that we have the weight, which is the red vector, pulling the system to the right, aka downward. And then we have a tension, again, in the string that's opposing that motion. So pretty basic here. We have f of g2 minus t1 equals m2a. And notice here the a is on the yellow side, and the a and the blue here do not have a subscript because they move as a system, so they share the same acceleration. So there's no need to denote A1 and A2 since they are the same. Okay, so if we just, again, basic substitution, the hanging mass has a weight, literally just the mass itself times the acceleration due to gravity, in this case, minus T1. So that's the first substitution there, replacing f of g2 with mg by definition. And then we substitute values in. The mass of the hanging mass is 4. G is 9.8. Again, do not plug in a negative value here because we take the line of motion to be positive. So pay attention to sign. If you do that, your algebra should come out pretty solid. And then, as you can see here, you have two unknowns. You have a T1 and an A. And the question is asking us to find A, right? So you can't really solve for it yet because to solve for A, you have to know T1. And this side, to solve for A, you have to know T2. So here you have, a couple of equations with multiple unknowns. So the next thing it's going to force you to do is set up torque. Again, you have three bodies. You have you have two masses and a pulley. So you do have to set up the physics for the pulley. In this case, just set up torque. To set up the net force or the net torque equal to the I alpha function. So if you pay attention, this particular diagram, T1 is going to want to cause the system to rotate clockwise, while T2 is going to want to cause the pulley to rotate counterclockwise. I went ahead and took the difference between them. Again, I'm taking the line of motion here to be positive. So T1 is going to cause a positive torque, subtracting the counter torque, which is T2. And then I replace the moment of inertia value for 1/2 mr squared because it is a disk, and the pulley is often referred to as a disk. And I replace alpha with A over R. And hopefully you know that function already because the relationship between A tangent and alpha, your angular acceleration is A equals R alpha. So that substitution is made there. And then I can go ahead and break up torque. By definition is the force, times the lever arm, which in this case is just R because in this diagram, T1 is already perpendicular to R, and so is T2. So it's T1 times R minus T2 times R. And then again, I kept everything on the right the same. So if you're paying attention to the math here, this particular left term, T1R minus T2R, has an R in common. So you can factor an R out. And then this R here, if you move it to the right side of the function, it's going to go on the bottom. And then this R on the bottom times R will give us R squared. And the R squares here will cancel out. So it leaves us with a function without R at all. Okay, so these two functions here can be now, or three functions, excuse me, can now be used. Okay, so if we can just do some basic substitution here, I carry this particular down. As you can see, all the R's in this particular pulley setup cancels out. And then all you have to do is substitute in for T1 and T2, which I have boxed here for you. Again, in no particular order there. So T1, again, it's right here. It's 39.2 minus 4a. Subtract, again, good habits. Use parentheses when you substitute. This way your signs aren't messed up. T2 itself is 5a plus 9.8. So I went ahead and put that in parentheses. This way you can distribute the negative sign to the 5a. Also, you need to distribute the negative sign to 9.8, which yields this particular next line. As you can see, there's a negative sign there. There's a negative sign there. Kids who are sloppy, if they don't use the parentheses, they might keep this as a positive sign, which will affect your outcome. So be careful again with signs. So here we have common terms, simplify stuff. 39.2 minus 9.8, and then we have a negative negative 4a minus a 5a, which pretty much gives us this next statement. So a negative 4a and a negative 5a makes a negative 9a, and then we just take the difference between 39.2 and 9.8. So if you do basic math and combine like terms, you get that 29.4 equals 10a because we moved the negative 9a to the other side. So 9 plus 1 is 10a, and to solve for a, we just divide. So there is your magnitude. I left all the units out here because the physics part is what I'm trying to teach you. So of course the unit here is meters per second square, and we take the line of motion to be positive. So the direction for this will be positive as well. Move on to B. For this one, it's just determining the instantaneous speed after it has descended 2 meters. So in the diagram, if M2 has fallen 2 meters, of course it's moving, and they want to know how fast that is moving. Again, just speed, so we don't really need to care for the direction. So one of the ways to do it is use common form. You already know that VI is 0 because the system is assumed to release from rest. It didn't mention anything about it initially moving. We just solve for A. So really substitute in VI is 0, and then I kept the right side the same. We just solve for the magnitude of the previous part A, which is 2.94. And if you just do basic math here, calculator work, you get VF square is equal to 11.76. But then to get rid of this square, you have to radical the right side. So if you do that, if V is going to be about 3.4, again, give take a little bit of rounding. I'm not really too concerned with rounding. I'm just trying to teach you the physics part. Another way to do it, is to just apply the average acceleration function. And since we're solving for VF, let's go ahead and manipulate the function so that it gives us that. VI here is 0. That's just, again, I put that as a placeholder for you to visualize there's a VI there, but in this case, it starts at 0. So to solve for VF, we need two quantities. We need an A and a T. Well, we already have A from part A, which is 9.4. And then we don't know what T is, but that's okay. Just go find T by utilizing given statements that you know for this particular problem. What we do know is the displacement, aka the distance that it has traveled. It states that it has fallen 2 meters downward. So you can just bust out the displacement function. I kept everything positive here because the line of motion is positive. The initial speed is 0. And then I wrote G here, but really it's not free falling, so it's not 9.8. So the acceleration should just be 2.94. So again, be careful here. I wrote G just as a general function, but it's not free falling, so you cannot plug in 9.8. You would just plug in whatever the acceleration is that you found in part A, which is 2.94. And if you do basic math and then square root the T square, you'll get that T is equal to about 1.17. And then from there, we can just substitute it back in the statement that we have on the left side. We have a delta T that we're missing, and we just found it. So just substitute it in, and then you'll get that VF. Again, it's about the same value, 3.4. So this is just variety. So far, there's 2 different ways to do it. Okay. So not to overwhelm you, but this is just to give you options. Or you can bust out the 2 average velocity functions. As you can see, by definition, average velocity is displacement over time. And if A is constant, which it is in this case, you can also do VF plus VI over 2. And the question is asking us to solve for VF. So just plug in stuff in that we know that it's fallen 2. Again, I don't get the -2 in this case because I took the line of motion to be positive. The time here is 1.17, which we just found up here. And then VI is 0, and then VF is really the only unknown. So if you manipulate the function, you get 4 over 1.17. And if you just complete your calculator work, you get about 3.4 as well. So far, there's 3 different ways to do it. And then last but not least, which I don't recommend, this is kind of tedious, just to kind of show you that you could though. We know that the relationship between linear and angular velocities by this function, V equals R omega. Okay. And then by definition, omega F is alpha T plus omega I. Again, that looks very similar to this right here. It's just applied in rotational stuff. And then we can just substitute. So V is equal to R, which I kept in the front. And then wherever omega is, in this case, this omega is omega F because omega I is 0. I can substitute it with just A T plus omega I because I just derived that. And then we know that omega I is 0. Again, I just wrote it as a placeholder. And then in this case, you can just substitute, okay? You don't know what alpha is, but again, you do know the relationship between alpha is A over R. So you can substitute alpha out for A tangent or A linear in this case over R. And then the R's will cancel out. And it leaves you with kind of the same thing as up here in blue. VF is equal to AT. which makes sense, which is the same function. So it all depends on how you see a problem and how you want to take this particular part. But it doesn't matter. You get the same again because a is 2.94, and then the time that you found is 1.17. So calculator work gives you about 3.4 meters per second as well. All right, move on to part C. This one says calculate the kinetic energy of M1. So to calculate the energy of the system after M1 has descended. So to calculate the energy of the system, you would just add them all up. So in my statement here, I have KE total is equal to KE linear plus KE rod, because again, the pulley, I misspelled pulley there, but that's okay. Plus KE linear. So you have three things moving. You have M1 moving down, the pulley is spinning itself on its own axis, and then M1 in green here is going to move to the right. So you have three things moving, which means they have to have their own KE. So therefore, write them all out. The first KE is for M1 because that's just moving linearly. So V has to be linear. The second term is for the pulley, which is 1/2 I omega square. And then the third pulley is M2, which is the hanging mass in blue. And that's just linear. So that's what it looks like. And then again, if you know your moment of inertia value for a disk spinning relative to the center of mass, the coefficient here is 1/2 M for the pulley, R square, and then we can substitute out omega square for V square over R square. So again, omega is just V over R, and the exponent there needs to be distributed to the V and also to the R. So it'll look like this in the next line. But if you distribute the R, the square to the R, it'll be R square, and the R square will cancel out. So in this next term here in the middle, you notice the R square disappear just from cancellation. Okay, and then everything else, you have M1. We just solve for V. V is 3.4 ish. Okay, so if you plug in all your values, which I did here, the mass here is 5. They all have the same V linear. And then notice here the coefficient here in front is 1/4 because a half times a half is 1/4. And if you do that, you get about 57.8 joules. Now the other way to do it, which I kind of like a little better, if you apply the work kinetic energy theorem. So in this particular system, the way I see it is that the system is moving because the weight of this object M2 is going to cause the system to fall down, aka accelerate to the right. But why it does that though, there's friction against the green box here, M1, on the flat horizontal surface. So if you apply your work kinetic energy theorem and not force anything, it should work out. So the work due to gravity for M2 minus the work due to friction, aka energy loss, should equal to the change in kinetic energy of the system. So if you do that, here's F of G2 times the displacement. I call this delta X, but it's up to you. You can call it delta Y or whatever the case might be. I take the line of motion to be, my X. So, but if you like Y, put a Y in there. It doesn't really matter. And then you would subtract the force of friction times the same displacement, because if the hanging mass dropped 2 meters, the box to the right, the green box also has to move to the right 2 meters as well. So really it's the same distance displacement. And then KI is 0. So really you're solving for KEF. And KEF in this particular instant represents KE of the system once once M2 is released and the system is allowed to accelerate. And if you do that, you get an answer of about 58.8. Now, if you look here, the answer up here is about 57.8. The answer down here is like 1 off. That's because the velocity here, it's really about 3.4 something. I just round down to 3.4. So because you're squaring it, technically, if you round the velocity to just more decimal places, your value will be a little closer than 58.8. So instead of getting 57.8, you get something a little bigger. But again, I'm not concerned with so much calculator work. It's just the physics I'm trying to teach you how to set up. Okay. And then for part D and E, I think these two were the quickest one out of them all. Part D says determine the number of revolutions it has completed after M1 has descended 2 meters. So if you want, you can just set up the angular displacement and for the pulley, because it's rotating, so it has to cover a certain angular displacement. And then omega I in this case is just 0. And again, you have to know the relationship between alpha and linear acceleration. Alpha is just a over r. So that basic substitution is made there. Everything else is the same. Again, I just put the 0 for omega i's. That's a placeholder visually there for you to see. So if you do math, A, we found in part A, which is 2.94. The radius in the statement is given. Again, whether you write this as capital R or lowercase r doesn't really matter to me. It's the radius of the pulley. And then the time we already solved in the previous part, which is 1.17. But don't forget the square. So if you do all that, you'll get about 40.25 rads. But you got to be careful here. The statement here in part D asks for a number of revolutions, not the number of radians. So you got to take this a step farther, and you got to make sure you convert 40.25 rads to revolutions. So the conversion for that is in this line. So you would start with 40.25 rads, and then for every 2 pi rad, that's 1 rev. Again, one revolution is 2 pi radian. So that statement is true. Again, the units for rads will cancel out. If you do basic math, it'll come out to be about 6.4 revs there. Or if you think like this, it'd be great. If M2 has fallen down 2 meters, that would indicate that the pulley has also rotated a linear distance of 2 meters. So this is what I would do if I was taking a quiz. I would just convert 2 meters to revolutions simply by saying each revolution is 1 circumference of a circle. And the circumference of a circle is just a linear distance. So this is 2 meters. The unit m for meters there is going to cancel out. And then 2 pi r, again, is just the linear distance, aka the circumference of a circle. But 1 circle is 1 rev. So if you do that, you should get the same answer as 6.4. Again, r is given in the original problem as 0.05. Okay, it's a lot quicker to do it this way. Hopefully you can see that. If not, stick with this side and just kind of crank it out. And then last but not least, part E. Part E asks for the angular acceleration, and this is light work. Again, the relationship between linear and rotational stuff is here for acceleration. A is equal to r alpha. We already know what A is from the previous part, and then we know what R is because it's given. So if you manipulate the function, A over R is equal to alpha, or alpha equals A over R, A being 2.94, R given as 0.05, and your answer is going to be about 58.8 rads per second square. And the direction, if you get technical, would be, I would say the best way to say it for this one, it'd be clockwise, because the pulley is going to spin clockwise because T1 is greater than T2 in this particular instant because the system's moving to the right. So the magnitude is 58.8, but if you want the direction, it is clockwise. Okay. And the other way to do it, which I don't recommend, again, is just make a point. You can use the information in part A when we set up the torque on the very right side of the chart, which gives you this statement, torque 1 minus torque 2 equals I alpha. And if you expand this to carry this down, again, the R is going to cancel out. You can factor out 1 R here on the left side because both these terms have an R. On this side, though, you have an R square, so be careful. So not all of the R's cancel, only one of them cancel. So if you pull an R out from here to here, it cancels one of these R's, which still leaves me with an R down here in the second line. And then from there, you can plug everything in, and you can just take my word for it. I crank everything on the calculator, and it gives you also 58.8. Again, I don't recommend this strategy. This is just to make a point.